Hello, everybody. Hi, I'm Adirani, and I'm a junior at South Brunswick High School, currently taking AP Physics C. And I would just like to thank you for coming to it's now our fourth live session, and just um, trusting me and my knowledge to help you all with preparing for the AP exams. Now, I really hope that this resource helps you, me and all of us ace this unique situation. And while I know that this is an unfamiliar time for all of us, I think that these live sessions will uh, really help us be the most prepared for the AP exams, which are fast approaching. Okay, without further ado, let's begin with our lesson for today. Today we will be looking at the AP Physics C electricity and magnetism portion of the exam. Now, last time, our second session, the last time we did the electricity and magnetism portion, we did a question relating to capacitors, dielectrics, the electric field. So that is one major portion of the exam, okay, the electric field and charge. Now we're going to be doing a question relating to circuits, which is another big part of the AP Physics C electricity and magnetism exam. Okay, so the question we're going to be doing is the second question from the 2010 exam, the 2010 electricity and magnetism exam. Okay, so let's pull that question up. Okay, so this is the question. And as always, if you have any questions whatsoever about anything that I do or say or anything that I write on the screen while I'm working, I kindly suggest that you use the chat feature. The chat feature is located on the bottom, okay, on the bottom of on the bottom bar, there will be a chat feature. Type your question in, and after each part, I will check the chat and answer any questions that you may have to the best of my ability. Okay, so I will be working through this question, and if you see anything wrong or anything confusing about what I did, just let me know in the chat, and after each part, I will check. Without wasting more time, let's get started. Okay, so this is the second question from 2010 exam, and let's read it. Okay, so in the circuit illustrated above, switch S is initially open and the battery has been connected for a long time. Okay, so we initially have an open switch and the battery has been connected for a long time. We know this information. And part A asks, what is the steady state current through the ammeter? Okay, and in case you might have forgotten, ammeter is a device that is used to measure the current at a particular point in the circuit, or at a particular point, the flow of electric charge. So this will be our ammeter. An ammeter is usually denoted by a circle with the letter A inside it for ampere or ammeter. Okay, so this is our ammeter. And part A asks, what is the steady state current through the ammeter? So steady state, so when you have a circuit, okay, when you have a circuit, any circuit, after a while, it reaches a constant state called the steady state. Okay, so after a long time, especially when you have other circuit elements like capacitors, okay, capacitors, which I'll highlight in blue. When you have capacitors and resistors, which I'll highlight in red, together, then there will be a unique steady state. Okay, there will be a steady state related to this circuit. So steady state happens when the capacitor is fully charged. Okay, so when you close a circuit, charge flows onto the plates of the capacitor and starts filling it up almost like a gas tank. Okay, almost like a gas tank. And once you can't put any more, then it stops. It won't take in any more charge. Okay, so one thing I like to do is when you're at a steady state after a long time, because a capacitor cannot be is not able to take in more charge, you can treat the capacitors like open sections, okay, like a gap in the gap in the circuit, okay, because it won't let any more charge through. Again, a capacitor works by charge coming and stacking on one side of the on the capacitor and the opposite charge being induced to the other. However, because a capacitor has a limit on the charge, once that limit is reached, no more charge can go through. It is blocked. So when you're at a steady state, um, when you're at a steady state, uh, at a steady state, the capacitor will act as a gap. Okay, nothing can go through. So what does this mean? It means that when you have current going through here, okay, when you have current going through here, well, it can't cross over here because the capacitor is full, okay, and it can't cross over here because over here the capacitor is full as well. So it turns out for part A, the steady state current through the ammeter will be 0 amps, 0 amperes. Okay, so that will be the current through the ammeter at the steady state. Now, let's go to part B, okay? Do we have any questions? Okay, seeing as there are none, we're going to go straight to part B. Okay, and part B asks us to calculate the charge on the 10 microfarad capacitor. The little sign before the F is mu and it means micro. Okay, so micro is 10 to the -6. So calculate the charge on this capacitor right here, 10 microfarads. Okay, now what is the at the steady state, what is the charge? Okay, well, the charge is given by this formula. The charge, oh, sorry about that. The charge is given by this formula. The charge is equal to the capacitance times the potential difference, or the voltage. Okay, so charge is given by the capacitance times the voltage between the capacitor, the potential difference between the plates of the capacitor. Okay, now we know the capacitance, and that's 10 microfarads. Okay, so what is our voltage? Now, when you're at a steady state, the reason that there is no current flowing, is that all the voltage has been sort of taken by the capacitor. The capacitor has all of the potential difference. Okay, when you look at, say, a purple loop like this, because there's no current going through here, because the capacitor is full, because there's no current, the voltage across this resistor is 0. Okay, however, the voltage must add up to the battery voltage. Otherwise, you have an unexplained loss of energy. Okay, so the voltage across the capacitor must be such as the voltage across the resistor and the voltage across the capacitor must sum up to the battery voltage, which means the voltage across the capacitor must equal 30 volts. Must equal 30 volts. So let's substitute that into our formula. We get our charge equals C times the voltage, and C is 10 microfarads, or 1 times 10 to the negative fifth. Again, micro is -6, so you have 10 times 10 to the negative 6, that's just 1 times 10 to the negative 5. Okay, 1 times 10 to the negative 5 farads. Okay, and our voltage, we just figured out, is 30 volts. 30 volts. And what do we get as a result? Well, we get 3 times 10 to the negative 4. Okay, this calculation can be done mentally. Okay, 30 times 10 to the negative 5 coulombs is 3 times 10 to the negative 4 coulombs. Okay, or you can write it as 300 microcoulombs. Microcoulombs. So that would be our charge across the on the one plate of the 10 microfarad capacitor. Okay, all we had to do was find the voltage across the capacitor using the fact that the voltage across the 40 ohm resistor, okay, the 40 ohm resistor on the upper left had to be 0 because there was no current going through it at all. Okay, so using this concept of the loop rule, that the voltage across the resistor and the voltage across the capacitor had to sum up to the battery voltage, we were able to find that the charge on the 10 microfarad capacitor had to be equal to 300 microcoulombs. Okay, so do we have any questions? Okay, we have no questions. So seeing as we have no questions, let's move on to part C. And part C asks us to calculate the energy stored in the 5 microfarad capacitor. Okay, so part C asks us to calculate the energy stored in the 5 microfarad capacitor. Now, the 5 microfarad capacitor, we have to look at it. Okay, it's on the lower left. Okay, it's on the lower left. And first we need our equation for the potential energy stored in a capacitor. Okay, and this equation will be found on the equation sheet. And this equation will be equal to, this energy will be equal to UC, where used energy, C is the capacitor. So the capacitor's energy will be equal to 1/2 times the capacitance times the voltage squared. Times the voltage squared. Okay then. Now, UC equals 1/2 C times the voltage squared. We know C, okay? We know C. So we don't know our voltage. Okay, C is given as 5 microfarads. But what is our voltage? Okay, now, if you remember from part B, we're going to use the exact same concept. Okay, and that is the idea of the loop rule. Okay, some people call it Kirchhoff's loop rule after the person who studied these circuit rules. Okay, Kirchhoff's loop rule, and what it basically says is that the sum of the voltages across any closed loop in a circuit must be equal to 0. Okay, it just has to be equal to 0, which means if you look at an arbitrary closed loop, okay, the battery supply. So we're going to use this one because this one's relevant. We're going to look at this green loop over here. Now the battery supplies energy by accelerating the charge or moving the charges through a potential difference. That potential difference is given by 30 volts. So that potential difference basically sends the charges on their way across the wire. Okay, now the charges, lose some of that potential energy, some of that energy by, well, by going on the capacitor and creating a potential difference there, and going through the resistor, which dissipates energy. Okay, resistors dissipate energy, okay, as heat, which means in order for all the energy to be accounted, the sum of the voltages have to be equal to 0. Now, the current through this resistor, well, at the steady state, we're assuming that the capacitors are fully charged, which means that there's no current going through the capacitor, which means there is no closed path. So the current through the 20 ohm resistor on the lower right must be equal to 0. Okay, so the current through here, okay, let's put in blue again, the current through here also has to be equal to 0. Okay, the current through here must be equal to 0. Now, because the current through the 20 ohm resistor is 0, that means the voltage across the 20 ohm resistor is 0. And because the voltage across the 20 ohm resistor is 0, the voltage across the 5 microfarad capacitor must be equal to 30 volts. Okay, and in order to account for the missing voltage, which was initially given by the battery. So what I'm saying is that the voltages of the capacitor and the battery must equal each other, okay, if the loop rule is to hold. Now, what does this mean? Okay, that means we have found our voltage and we have found our capacitance, meaning that at this point, we're essentially plugging numbers into a formula. Okay, so we have 1/2 C times delta V squared. Okay, so 1/2, well, it's a 5 microcoulomb capacitor, so we have 5 times 10 to the negative 6 farads. Okay, that's the capacitance, okay, of our capacitor that we're looking at. Okay, and the potential difference, the voltage will be given by 30 volts, okay, as we found earlier. So this will be 30 volts, and then we square that, 30 volts squared. And what does that give us? Well, this gives us, if we substitute into a calculator, we get, okay, we get 2.25 times 10 to the negative 3 joules. Okay, energy is written in joules. Okay, and you can write it in multiple ways. You can write it as 2.25 millijoules. Okay, that's one way you can write it. Or you can write it, if you want to keep up with the micro convention that we've been using for charge and capacitance, you can write it as 2,250 microjoules. And that is it. That is the energy. Stored in the 5 microfarad capacitor. Now, we're going to erase this. So if you need to just draw these in for a bit, you should draw them, okay? Because now we see a different situation, okay? So I'm just going to erase this and clear the clutter, okay? So the switch is now closed and the circuit comes to a new steady state. Okay, so this switch, which was open before, is now closed. Okay, closed. So now that section of the wire is complete. Okay, so part D asks us, calculate the steady state current through the battery. Now, you might be thinking, okay, from the first three parts, all the currents that we've been looking at have been equal to 0. So some may be tempted to just write in 0 amperes. Okay? However, the fact that the switch is now closed changes everything. And let's see why it changes everything. Well, before, when the switch is open, when charge was leaving the battery, it couldn't get anywhere, because think of like the capacitors as like massive like canyons with no bridge. There's no bridge, so you can't cross. Okay, so like a cliff with no bridge attaching to the other side, you can't cross. Okay, the switch was open before, so you can cross through that section of wire as well. However, now the switch is closed. So if you look at the circuit properly, you might see that there is a way for the charges, for the current to go back to the battery. Okay, and it's through this loop. I'm going to highlight in yellow. Okay, so charge will go like this, right? It will go here, go through the resistor, and now because the switch is closed, this section of the wire is complete. Okay, the bridge has been fixed. Okay, if you imagine like a drawbridge, okay, in like a castle, you have a drawbridge where you press a lever and the bridge will go down. The fact that the switch is now closed means the bridge is down and current can cross over. Okay, we'll now go through this resistor and go back. So, in fact, the fact that we close the switch means that we have, in fact, completed the circuit. We have completed the circuit, even in the steady state. Okay? And notice how none of the charge goes through the capacitors. It's because the capacitors are full. So in that section of the wire, current does remain 0. So in the ammeter, the current will still measure, it will still read as 0. However, that doesn't mean there's 0 current everywhere. Because whenever there is a closed path, well, I can imagine the charges, they want to get their energy back. They will try to find a way in order to get back to the battery and get accelerated through that potential again. So by closing the switch, we found ourselves a closed path. So we can regard this yellow path as our circuit right now. Okay? So when you look at part D, okay, what is the steady state current through the battery? Okay, well, now if we treat this as a simple resistor circuit, because remember, we can ignore the capacitors as gaps, like open holes in the circuit. Okay, we can completely ignore them since they're fully charged. It's the steady state. Okay, so now we can treat this as a simple resistor circuit. So what's the total resistance? The total resistance is the sum of the individual resistances, because in this yellow path, it turns out that these resistors are in series. Okay, they are in series. They're right next to each other rather than on a separate branch. Okay, the current doesn't split at any point, meaning that the resistors are in series and you just simply add them. Okay, just simply add them for equivalent total resistance. Okay, I like to write RT for total resistance, also known as equivalent resistance, and we get 40 ohms plus 20 ohms. 40 ohms plus 20 ohms is equal to 60 ohms. So that will be our total equivalent resistance. That will be our equivalent resistance. And now, okay, and now we find our current. We find our current. We have our current, and now we use Ohm's law. Okay, Ohm's law is a big, super important law regarding circuits. Okay, and it relates the current, the voltage, and the resistance all together. And it basically says that the current through a circuit is directly proportional to the voltage. And I write this E because it's a battery and it provides an EMF. Okay, and EMF is basically the same thing as a voltage. I just prefer to write E for a battery voltage. Okay, that's just my preference. Okay, so the battery voltage. Okay, so the current is directly proportional to the voltage divided by the resistance. Okay, the total resistance. Now, in actuality, this E wouldn't necessarily be the battery voltage. The voltage is referring to the voltage across a resistor. However, the reason why we did this total resistance step is that now we can treat the sum of the 40 ohm resistor and the 20 ohm resistor as one single 60 ohm resistor. And that's really easy because by the loop rule, Kirchhoff's loop rule, the voltage across the 60 ohm resistor is automatically equal to the battery voltage. And I just implied all of that by writing E at the top. Okay, so we have E over RT, and this is 30 volts over 60 ohms. Over 60 ohms, and that is equal to 0.5 amperes. 0.5 amperes. So there is a non-zero current now because we have closed the circuit. Okay, we have closed the circuit. So note that even though every steady state does not necessarily imply zero current, okay? Steady state is just a state reached after all the capacitors have been charged, or after a really long time will start to come steady. There won't be any huge changes in current and voltage, okay? So this will be the situation after a long time the switch is closed, okay? Now let's move on to part E. Okay, let's see if there are any questions. Do we have any questions? All right, seeing as there are none, we can now move on to part E. Okay, and part E asks us to calculate the final charge on the 5 microfarad capacitor. The 5 microfarad capacitor. Now, this situation is different. You have to recognize that. So you can't use any of the same quantities from parts A, B, and C. This situation is completely different. But it shouldn't really be worrying because it shouldn't really be worrying if you know what exactly you should do in this situation. Okay, so let's just see how we should approach part E. Now, let's write down our equation. And the reason why I like to do that is now I can see concretely what quantities we are missing. So the equation for charge on a capacitor is equal to the capacitance times the voltage across the capacitor. Okay? Now, we have our capacitance, 5 microfarads. Okay? 5 microfarads. However, what is our voltage? Now, how would you approach this section? How would you approach this? Well, in order to find the voltage, you have to realize that, first of all, it's not the same concept as part C. The voltage is not equal to 30 volts. If you take 30 volts as your voltage, you will get it wrong. Because in part C, where we last found the voltage of the 5 microfarad capacitor, the current through the 20 ohm resistor we assumed to be 0 because the switch was open. Okay, there was no closed path around the circuit. The circuit was not closed. Okay, so there was no current through the 20 ohm resistor. However, in part D, we just found out there was a non-negligible current through the 20 ohm resistor. Now what we're going to be doing is trying to excuse that. Okay, what we're going to be doing is trying to utilize what we know, given that now there's a non-zero voltage across the 20 ohm resistor. Now, let's use Kirchhoff's loop rule, the same rule we've been using for this entire time, okay, to find voltages. So let's look at this loop over here, the one I'm highlighting in purple. Okay, so this is our loop that we're going to be looking at. And remember, this loop rule holds for any loop, any closed path in the circuit. So this loop is technically allowed. Even though there's no current going through half of the loop, this loop is allowed. Any closed path around the circuit, the sum of the voltages has to equal 0. Okay? Now, what is the voltage? What is the voltage across the 20 ohm resistor? Because if we know the voltage across the 20 ohm resistor, then by Kirchhoff's loop rule, we can see that the voltage across the capacitor has to be equal to the battery voltage minus the voltage across the resistor. Now, the voltage across the resistor can be found using Ohm's law. Ohm's law that we have used earlier. Now, instead of finding the current as we did in part D, we're going to find the voltage across the resistor. So, the voltage across the resistor, okay, let's make it a little more clear. Okay, so the voltage across the resistor is equal to the current to the resistor times the resistance. Now we're looking at the 20 ohm resistor, and there is a current of 0.5 amperes going through it, as we found in part D. Okay, now the resistance is 20 ohms. The resistance 20 ohms. That's what we found. That's what we're given. So resistance is 20 ohms, and the current 0.5 amperes. So we get 10 volts. 10 volts. So that is the resistance across the 20 ohm resistor. Sorry, that is the voltage across the 20 ohm resistor. Okay, just the 20 ohm resistor. Now, by the loop rule, the sum of the resistances the sum of the voltages must be equal to 0. So the battery supplies a voltage, so that's positive. Okay, so that's positive. Okay, we lose some voltage due to the capacitor, and we have 10 volts. We have 10 volts due across the resistor. Now, we just solve this equation. Okay, so we solve this equation, 20 volts minus the voltage across the capacitor must be 0, and we get the voltage across the capacitor is 20 volts. Not 30 volts, but 20 volts, because there's a current going through the 20 ohm resistor that we have to account for. Okay, now we have our voltage, and now we can easily find the charge. Charge is equal to the capacitance, which was 5 microfarads, times 20 volts. And we get 1 times 10 to the negative 4 coulombs, or 100 microcoulombs. Okay, let's go to the final part, part F. Work through part F right here. Part F asks us to calculate the energy dissipated as heat in the 40 ohm resistor in 1 minute once the circuit has reached steady state. Now, energy dissipated is also the product of the power, the rate at which energy is being dissipated, times the time interval. Okay, and the power going through the circuit element, okay, I'm running a little short on time, okay, but the power through a circuit element can be written as I squared R. I squared R, okay, and this will be found on the equation sheet. Okay, it's a standard equation times T. And now we're just plugging in numbers. Okay, 0.5 amperes squared times the resistance, 40 ohms, times the time, which is 60 seconds. Again, everything has to be in seconds, not a minute. We can't put 1 minute in there. Okay, and what do we get? Okay, we get 600 joules. 600 joules. So that's how much energy is dissipated as heat due to the current. So let's see, are there any questions about any part of this problem? Do we have any questions at all? Okay, so seeing as there are none, we're going to end this. Okay, thank you so much. And this problem wasn't all that hard. Okay, did test a couple of tricky concepts because circuits is, however easy this may seem, it is a bit hard conceptually visualizing how the charge flows through the circuit, how it flows and how it behaves in a circuit. So it's a little tricky to visualize all of that, but a positive is if you understand how everything works and how the current flows in a circuit, the equations are very easy. Okay, the equations are very, very easy. Okay, so thank you. We have a message. Thank you for doing these sessions. It helps. Thank you for attending these sessions. These sessions are designed to be helpful. Okay, they're designed to be helpful. Okay, so let's go back. Okay, so thank you. Thank you so much for coming to this session. I am so glad that all of you were able to join this session. Okay, this is our 4th session. I'm looking to hold another session, okay, probably the same time, most likely tomorrow. Okay, I'll have to see, but please do leave feedback and suggestions on today's session so I can make these better each time. Okay, so next session, we're going to be doing mechanics. Please leave comments on what I should cover next in mechanics. I will try to upload this session onto Facebook or or if that doesn't work, YouTube. Okay, thank you so much and goodbye.